Today we're going to be talking about data models for exponential and logarithmic functions. And so if you'll just take notice here, these are the 5 most common types of mathematical models involving exponential functions or logarithmic functions. And so most of the problems that we will be working through today look like one of these 5 equations in some form or fashion. And so I'll try to make sure that I point back to this list so that as we work through some of these equations and solving these, you can relate them back to which model this might be, because all of these graphs look a little different. And so I just want you to know there's 5 different ones. We're going to be working through several of them today, solving data models, which is basically, math language for word problems. Now that we have the skills to solve exponential and logarithmic equations, a lot of this is going to be setting them up and solving them today. And don't forget our compound interest formula as well. And so our compound interest formula is where we're going to start today. And, in the past, what we've done is they've given us an initial investment, they've given us the rate, and then they've asked us to calculate how long does it take for it to double, or how much money is in there after X amount of years. And so today we're actually going to they're just giving us little pieces in each one, and we're actually supposed to figure out how to set them up, what it is that we're going to be solving for, and then solve it. And so if you'll look at the very first one, we've got an initial investment of $7,500. We do not know the rate, but we do know that it takes 21 years to double in an investment. And so what we don't know is how much is left after, or how much we have after 10 years. And so first off, start by writing the formula down. We have A equals P e to the RT. Okay, and so the very first one, what I'm going to do is I'm going to go ahead and fill it in with what I do know, and then I'm going to solve for what I don't. And so first off, if I know that my initial investment is $7,500, that's going to be my principal, my P. Now, if I am looking at doubling, all you're going to do is double that $7,500, and that gives me $15,000. So I know that in the end, I'm going to wind up with $15,000. And then E to the RT. We don't know the rate, and so that is the thing that we're going to be solving for. But we do know the time that it took to double. It took us 21 years to double it. And so I'm going to say 21R. Now all I'm going to do is I'm going to solve for R. So we start that by isolating. You want to isolate the exponential. So we are going to try to get e to the 21 times r by itself. And how we're going to do that is divide out the 7,500. So divide both sides by 7,500. Now, of course, we know 15,000 divided by 7,500 is 2, because we know we were doubling. So 2 equals e to the 21r. Now think about this, back to our solving equations. I am looking for r, which is in the exponent. Okay, and so think about how would I solve for a variable in the exponent. And you're going to do that by taking the log of both sides. Now, because we have an e in our problem, we're going to take the natural log of both sides. So this is going to become ln of 2 equals ln of e to the 21r. Now, the whole purpose of us taking the log of both sides is because what I'm solving for is in the exponent. and I'm going to use my exponent rules to go ahead, or my log rules to drop that down in front so it's no longer an exponent. So what I've got is I'm going to ln of 2 equals 21r ln of e. Now remember, ln e goes to 1. So I've got ln 2 equals 21r. Divide by 21, divide by 21, and you get your rate, which equals, so in your calculators you'll want to type in ln of 2 divided by 21, and that gives us 0.033. Now, that is my rate in decimal form. Percent-wise, because if you notice it says annual percent rate, so we want to make sure we write that as a percent. So remember, when you're taking it from a decimal to a percent, you move it 2 places to the right. And so my percentage is 3.3%. So I have filled in one of my blanks, 3.3%. Now what I want to figure out is, now that I know my rate, I can actually solve for how much money I have after 10 years of compounding it continuously. So now I'm going to do A equals PERT again, but this time I don't know what A is. Okay, so I'm going to leave A alone. I do know I started off with 7,500. And then I've got E to the, I know my rate now, so 0.033 times 10 years. So this one is similar to the ones that we did at the very beginning, where we're just plugging in a years. So when you plug that into your calculator, you get $10,432.26. So after 10 years, I have $10,432.26. So I have completed the first line. Now I'm going to go ahead and I'm going to work on the second row. So now they're changing the initial investment from $7,500 to $5,000. We don't know the rate. We don't know how long it took for it to double. But we do know that after 10 years, we have $5,665.74. So what I'm going to do is I'm going to, again, plug in the information that you know. So I know that I have $5,665.74 as my final answer after 10 years. And I started off with 5,000. I don't know my rate, so my R is what I'm going to be looking for, but I do know that after 10 years, that's what I have. So now we're going to use the information we have to solve for R. In all of these problems, however you set them up and whatever it is that you're finding, you should only have one variable that you're looking for. If you plug everything in and you have 2 variables that you're still looking for, then you've missed something. So, first thing, remember, to solve for R, I've got to isolate the exponential, which means I'm going to go ahead and divide out the 5,000. And that's going to give me 1.13 equals e to the 10r. And then think about from here, in order for me to drop that 10r down, I've got to take the log of both sides. So I'm going to take the natural log of both sides because of the e. So I have got ln of 1.13 equals ln of e to the 10r. Now using our log rules, again, we want to drop that 10r down in front. So ln of 1.13 equals 10r ln e. My ln e goes to 1. Don't say it cancels. Some of you guys have been saying that, you know, the ln(e) cancels. It's not that it cancels, it's that the whole ln(e), it goes to 1. So now all I have to do is divide by 10. So in your calculators, you're going to go ahead and type in ln of 1.13 divided by 10, and that's going to give us our rate, and we get 0.012. So that's in decimal form. That's what we're actually going to use in our formula, but as far as writing it in the chart, we're going to move it 2 places to the right. It's actually 1.2%. So we have a rate of 1.2%. Okay, now we're going to go back and we're going to look at how long is it going to take for us to double the time, or for my investment to double. So I'm going to set up my problem. I know if I'm doubling my investment and I started off with 5,000, then that means in the end I'm going to end up with 10,000. My initial investment was 5,000. E to the, we know R now, we know it's 1.2%. So I'm going to go ahead and write 0.012. Now, what we don't know is we don't know T. We don't know how long it's taking for my investment to double. So again, what we're looking for is in the exponent. So we're actually going to solve this the exact same way we solved that one. Go ahead and divide out the 5,000. And that's going to leave me with 2. So I've got 2 equals e to the 0.012t. Now again, in order to solve for something that is in the exponent, I need to take the log of both sides. So I'm going to go ahead and do that. ln of 2 equals ln of e to the 0.012t. And then again, we can drop this down in front. ln of 2 equals 0.012t ln of e. ln of e goes to 1. And now all I have to do is divide by 0.012. So in your calculators, you're going to type ln of 2 divided by 0.012. And we get 57.8 years. So it's going to take me 57.8 years to double my investment with when I have a rate of 1.2%. That's going to take a long time. So 57.8 years. All right, now we're just down to the last one. So I don't know what my initial investment is. That's something that I'm going to solve for. But I do know the rate is 4.5%, and I do know that after 10 years I have $100,000. So I'm going to go ahead and use my formula and plug in what I know. So I have A equals PERT. Now, I don't know my initial investment. What I do know is I wind up with $100,000. I'm looking for P. I also know my rate. My rate is 4.5%. So 0.045. And I do know 10 years is what it took. After 10 years, I had $100,000. So I'm going to use 10 for T. So what we've got here is you've got 100,000 equals P to the E to the 4.5. Now, E to the 4.5 is just a number. So I'm going to just go ahead and instead of actually plugging that into my calculator, I'm going to go ahead and I am going to just leave it E to the 4.5 so it's more exact, and just divide E to the 4.5. Just like you would if that number was like 10,000 or whatever. You would just divide it out to solve for P. So in your calculators, you're going to type in 100,000 divided by E to the 4.5. And that's going to give us, and of course with money, you round to 2 decimal places down to the cent. So I'm going to say that I had initially $63,762.82. So that was the initial investment. So I'm going to go up here to my chart. I'm going to fill it in. I had $63,762.82 to begin with. So then let's think about, okay, now we want to know time to double. So first off, in setting my equation up for doubling it, I'm going to take this and I'm going to go ahead and multiply by 2 and get what the doubled amount would be. And that's going to be 127,525.63 equals $63,762.82. E to the, we know the rate is 0.045, and what we don't know is how long it's taking to double, so we're looking for T. So again, because what we're looking for is in the exponent, we're going to isolate our exponential. So I'm going to divide out the $63,762.82. And of course, we're going to wind up with 2. So we've got 2 equals E to the 0.045 T. Take the natural log of both sides. ln of 2 equals ln of E to the 0.045 T. Drop that down in front. So ln of 2 equals 0.045 T ln E. ln E goes to 1. So then all we have to do is divide out the 0.045. So in your calculators, you're going to plug in ln of 2 divided by 0.045, and we wind up with a time of about 15.4 years. So it takes us about 15.4 years to double our investment with that rate. So 15.4 years. And so on your homework, you're going to be given various scenarios with the compound interest formula, and you're going to be expected to be able to solve for whatever is missing. Now we're going to move on to example 2, where we're talking about radioactive decay. Same thing, it says complete the table. So again, you're just going to use the formula, and you're going to plug in what you do know to solve for what you don't know. Now, I didn't give you the formula on your formula chart, so I'm going to go ahead and give you that. Now, half-life is half of C equals C E to the KT. And then we've got our regular formula, which is C E to the KT. Kind of similar to our compound interest formula. So first thing we're going to do is we're going to start off with the half C equals C E to the KT formula. 1/2 C equals c e to the k. Now, as far as time goes, I know the half-life is 1599. So I'm going to go ahead and plug that in. Now, your c's will cancel. So that leaves us with 1/2 equals e to the 1599k. And I'm looking for k. I am going to take the log of both sides. So that's going to give me ln of 1/2 equals ln of e to the 1599k. And again, use your exponent rules. We're going to drop that down in front. So ln of 1/2 equals 1599k ln e. ln e goes to 1. Divide by 1599. And that will give us k. ln of 1/2 divided by 1599. I wouldn't plug that into a calculator because then you're going to be rounding and then that could create a rounding error. So what I'm going to do is I'm going to use the k value, if you notice here. Now I'm going to move over to this formula, my actual formula for radioactive decay, and c is going to be my initial amount, and then k is that number that you have to use, and then t is for time. So I am going to go ahead and plug it all in exactly, and that way it leaves no error for rounding. So this is what I'm actually going to plug in for my k value. Now, you could plug it in and go ahead and get a rounded answer, but the thing is you just want to make sure that you can be as exact as possible. So if you can use the exact number, go ahead and do that. Okay, so that means that in my exponent for k, I have ln of 1/2 divided by 1599 times 1000. And of course, your calculator will do all of that. You just have to be very careful. Make sure you use parentheses. Make sure you have plugged it in exactly right. So, how much of the amount do we have left after 1,000 years with a starting amount of 10 grams? So when you plug all of that into your calculator just exactly as it is, you get 6.48. So I know my amount after 1,000 years is about 6.48 according to the half-life and the numbers that we have. Okay, so another way that they use these is with populations. So demography. So if we look here, we've got population in thousands. Now, be very careful because when you're reading your problems, you need to make sure you note significant things like that. Okay, so in thousands, we're going to be getting answers, but then remember, that's going to be that many thousands of people. So the population P of Pittsburgh, Pennsylvania, from 2000 through 2008 can be modeled by that function, where T is the year, with T equals 0 corresponding to the year 2000. So it says, according to the model, was the population of Pittsburgh increasing or decreasing from 2000 to 2008? Now, we don't have to do any math in order for us to be able to look at this and be able to tell. Now, if you had to just look at that function and guess, is it increasing or is it decreasing, what would you guess? Because of the negative in the exponent right there, I would always guess that it's decreasing. And I'm going to say that, decreasing. So the population is decreasing because of the negative exponent. And so now what they're doing is they're asking us to calculate populations in certain years. So remember, this is when we're using t equals 0. So this would be when we would use t equals 5, and this would be when we would use t equals 8. So all I'm doing is I am plugging in for t, and I'm solving for the population. So 333.68 e to the negative 0.0099 times 0. So there's for the year 2000. Now when you plug all of that into your calculator, you're going to get 333.68. But remember, back to our original problem, it's not 333 people, 333.68 people. It's 333.68 thousand people. So just be sure in your answer that you indicate that, because if you were to just write this and circle it as your final answer, I would count it wrong because you have not told me that it's that many thousand. I need to know because that's a big difference. 333 is not the same as 333,000. On to the next one. So again, you're just going to take the formula they give you and you're going to plug in 5. So e to the negative 0.0099 times 5. Plug it in exactly as you see it, and that's going to give me 317.56 thousand people. And then I'm going to go ahead and I'm going to let you do the last one. So set up your formula, plug in 8 for the year 2008. I'm going to go ahead and write what you will get. You get 308.27 thousand people. But go ahead and plug it in, set it up, and see if you can do that one on your own. Okay, so now what it's asking is when will the population of Pittsburgh be approximately 290,000? So what I'm going to do is I'm going to set this equal to 290. Now, why would I set it equal to 290 and not 290,000? Remember, in the information that they gave us, they said this was representative of thousands of people. So we need to make sure that it's corresponding with what we're plugging in. So I'm going to go ahead and divide out 333.68, and you get 0.87 equals e to the negative 0.0099t. Now what do we do from here? We take the natural log of both sides. So ln of 0.87 equals ln e to the negative 0.0099t. Drop this down in front using our log rules. So we get ln of 0.87 equals negative 0.0099t lne. Our lne goes to 1, and you divide out negative 0.0099. So in your calculator, you need to plug this in, and you will get t. You get about 14. So you're going to have to round. And when you do, you get about 14. Now, 14 is not my answer. That doesn't make sense in the context of the problem. It says, when will the population be approximately 290,000? It's not at 14, it's at the year 2014. So make sure on all of these problems that you are reading carefully the problem and doing what it says, not just getting an answer, because when you get the answer, that doesn't really make sense in the context of the problem. So you really have got to be careful on these word problems and pay attention to what the final answer is asking you to do. Now we're going to look at a problem with biology. We've got the number of yeast organisms in a culture given by this model. And so it says graph the model. Now, first off, we've been harping lately on graphing models. Remember, most of the time you're going to just be graphing that first quadrant. Now, it's telling me the x-axis, which is time, in hours. So be sure you label 0 to 18. See, it's nice because here they're actually giving me what they want me to set my x-axis at. So do it. Make sure you label and you also number your axis. So when you're showing me a picture of the graph, it's an accurate model in the context of the problem. And then I'm going to go ahead and tell you, we're going to go, up to about, 800 would be a good place. So you're going to want to set your window from 0 to 18 on the x min 0, x max 18, y min 0, y max 800. Now, I haven't labeled this one yet, so I'm going to say number of organisms. Okay, so that I understand. Now, if you look at the graph, it goes something like this. Okay, so that's giving me an accurate graph when you use the appropriate x and y axis numbers. Now it says, use the model to predict the populations for the 19th and the 30th hour. And so what we're going to do is we're just going to plug in 19 and 30 in for t and solve. So y equals 663 over 1 plus 72 e to the negative 0.0547 times 19. So get your calculators out. Now be sure and put in your calculators, make sure you put the whole bottom in parentheses or it will not give you an accurate answer. And when you do that, you get about 661.54 for the 19th hour. So again, make sure in your answer you're telling me, okay, not just 661.54. I have no idea what that was. Was it for the 19th? Was it for the 30th? So be sure and indicate in your answers, if you're being asked to find multiple things, that you label what each one is. So then again, do it for the 30th hour. So again, in parentheses, the whole bottom in your calculator, e to the negative 0.0547 times 30. And when you plug all of that in, you get about 662.99 for the 30th hour. And that's going to be my two answers for that part. Now it says, what is the limiting value of the population? And so if you notice, back up at our graph hits it goes up, and then it hits like a peak. In other words, an asymptote. So there is an asymptote that you can't see that is at some value. And so what you've got to do is you've got to figure out what value that is. Now, if you're looking at the model itself, eventually all of that is going to go to 0. So if all of that, as time goes on, as time gets bigger and bigger and bigger, that number is going to get closer and closer to 0. And so if you look, we've got 663 divided by 1, and so we're going to be able to tell this goes to 663. That's going to be the limiting value of the population. So in other words, that would mean that we have a horizontal asymptote at y equals 663. Now it says, why do you think this population of yeast follows a logistic growth model instead of an exponential growth model? So let's go back up to where our formulas were. Now it says, why does it follow a logistic growth model instead of an exponential, whoops, wrong one, an exponential growth model? And the reason is simply just because exponential models have unrestricted growth. Like it's going to keep growing and growing and growing forever. Its graph looks like this. Now, the logistic growth model looks something like this, where it's going to hit a plateau and it's going to peak out at a certain value. So it's all about the fact that in an exponential growth model, we wouldn't have a horizontal asymptote. So you can just say something like, exponential growth models have unrestricted growth. In other words, there's no asymptote that's going to cause that to plateau out. Whereas logistic models grow, they do grow exponentially, is what it looks like. So like if you didn't have all of the graph showing, it would look to you like it was growing exponentially. Logistic models grow exponentially at first, but cap off at a certain point. And so you can just know that's the difference between those two types of graphs. Okay, now we are on to earthquakes. And so they use log models to measure the magnitude and the intensity of an earthquake. And so this right here is the equation that they give us, the Richter scale. And so you guys have heard, in earthquakes, they have a certain measure. If a certain earthquake is really, really intense, it's going to be upwards of like 7 and up on the Richter scale. And so they measure that with this equation. And so let's look at part A, where it says, in 2009, Greece experienced an earthquake that measured 6.4 on the Richter scale. And then also in 2009, Indonesia experienced an earthquake that measured 7.6 on the Richter scale. Find the intensity of each earthquake and compare the two intensities. And so what we're going to do is we're actually going to plug in. So I'm going to make Greece over here. And then I'm going to make Indonesia over here. Now, what I'm going to do is I'm going to plug in for I naught, you're going to use 1. And then we know that R equals 6.4. And so those are the values that we're going to plug in. We're going to plug in I naught, we're going to plug in a 1, we're going to plug in 6.4 for R. So 6.4 equals log base 10. So just a regular log on your regular log base 10 of I, that's what we're looking for, over 1. And so then I've got to figure out how do I solve this for I. Now I divided by 1 is just I. So this is what I really have. Now remember, how do you solve a log equation? You change it to exponential form. So I'm going to actually change this to exponential. So by do that, you remember you make little b become big B. So 10 to the 6.4 equals I. And there you have it. So you could multiply this out and you would get a really humongous number. And that's okay, you can do that. I'm just going to leave it as 10 to the 6.4. Now, I'm going to come over here and I'm going to do the same thing for Indonesia. So remember, I'm using I naught, I'm using 1, because that would be, you know, the lowest it would measure on a Richter scale, the lowest measure. And I know that mine was 7.6 in Indonesia. So 7.6 equals log base 10 of I over 1. So 7.6 equals log base 10 of I, and then change that to exponential form. So we've got 10 to the 7.6 equals I, and that's for the one in Indonesia. Now what it's asking us to do is to compare the two intensities. So what I'm going to do for the comparison is I'm actually going to find the ratio. So I'm going to do 10 to the 7.6 over 10 to the 6.4 and see what that gives me. It gives me approximately 15.8, which is about, if I rounded to a whole number, 16. So what we can say here, and this is what I want you to write out, is the earthquake in Indonesia was 16 times more intense than the one in Greece. And that's all that means. All right, now we are to the last example, culinary arts. And so here we have another model, and it says you take a 5-pound package of steaks out of the freezer at 11 a.m. and place it in the refrigerator. Will the steaks be thawed in time to be grilled at 6 p.m.? Assume that the refrigerator's temperature is 40 degrees and the freezer's temperature is 0 degrees. Use the formula for Newton's law of cooling. So that formula is Newton's law of cooling, where T is the time in hours, and T is big T is the temperature of the package of steaks. So what I'm going to do is I'm just going to plug in what I know. Now first off, I know how much time has elapsed because I know I've gone from 11 a.m. to 6 p.m. So if I'm letting 11 a.m. be 0, how many hours does that mean has gone by? 7 hours. So I'm going to go ahead and I'm going to plug in 7 for little t. Negative 5.05 ln of t minus 40 over 0 minus 40. Now, so basically what I'm trying to figure out is I'm trying to figure out what will the temperature be after 7 hours. And so I'm going to go ahead and solve this for t, and then if my t value, notice, okay, so think about thawing it out. If it has thawed out, then that means it has reached the temperature of the refrigerator, which would be 40 degrees. So what my goal is I want that temperature to be 40 degrees. If it is anything less than 40 degrees, then we'll say no, it hasn't thawed. So go ahead and solve. So first thing I'm going to do is divide out negative 5.05. And I'm just going to leave it like that because that's a very long fraction, a very long decimal. So 7 divided by negative 5.05. And I want to make sure I have it as exact as possible. ln of t minus 40 divided by, now 0 minus 40 is just negative 40, so I'm going to go ahead and write that on the bottom. Now what I've got to do is I'm going to change this to exponential form in order to solve for t. So remember, the base of a natural log is e. They're not going to write it, but that's what it is. So what I'm going to do is I'm going to say little base, so e becomes big base, 7 to... So e to the negative 7 divided by 5.05 equals t minus 40 divided by negative 40. And now think about how would you solve for t. So I'm going to put this under 1. It's like you cross multiply and divide. So I'm going to cross multiply and I'm going to divide. So e to the negative 7 over 5.05 times negative 40. So I'm going to go ahead and just write negative 40 in front. Equals t minus 40 times 1, which is just t minus 40. So now to solve this, I'm going to add 40. Negative 40e to the negative 7.505 equal, oh, whoops, plus 40 equals t. So now we can plug all of that into our calculator, and because we have no rounding up to this point, it's going to give us a really accurate answer. And so when you plug all of that into your calculator, negative 40 times e to the negative 7 divided by 5.05 plus 40, you get about 30 degrees. So my temperature is 30 degrees. So the question was, is that thawed in time? And the answer is, if it hasn't reached 40 degrees, the temperature of the refrigerator, then the answer is no, it hasn't thawed in time. So I'm going to go ahead and answer the question with no. In 7 hours, the steaks will be 30 degrees, not 40 degrees. So it still has 10 more degrees to go before it can be considered thawed out. And that's my final answer. And this takes care of our exponential and log modeling.